Hello, everyone. This is Edward Doolittle here with your last final installment of Math 101 Set Theory and Systematic Counting, is what I'm going to talk about this time. And this will be it for the course. We also have a quiz that's coming up, quiz number 5. And let me see, what shall I put on quiz number 5? We will put on the conversion of well, we'll have to put on some stuff about fractions. So there'll be fraction operations, Lewis terms, conversion of fractions to decimals. Okay, so this will be quiz 5. And I will upload it soon. I was hoping to do that on Thursday, but time is passing. This is probably Friday or Saturday before I get the quiz up. So sorry about that. But anyway, it'll be last quiz. So that is old material now. New material is set theory and systematic counting. Let's get on with it. It is found in the course textbook in an odd place, page 2-10. So it's early on in the course textbook, and it's in the section on subtraction, which I find to be a bit odd. So I put it in a different section all by itself. I've put it into the I'm putting it into this final section, set theory. There's also logic in the course, but we're not going to have time to get around to logic. So set theory is just going to be a whole unit on its own, and this is going to be the only lecture in that unit. So the idea of set theory is that there's some kind of universe, and it's not the real universe that it's not everything in the whole real universe, but it is a kind of a working universe that we have. It's the universe of discourse, so whatever is the subject of our investigation. So it may be students in our Math 101 class, for example. In that case, our universe just has about 35 individuals in it. And then within this universe, we have different kinds of collections. We often put our universe, represent our universe as a rectangle, and within that rectangle there are collections. So everybody who likes chocolate ice cream could be this set, and we're going to give it a label A. So this group or collection or set of individuals who likes chocolate ice cream is the set A. And now what we're going to do is look at a few ways of combining sets, set operations if you wish, and then look at counting and trying to figure out how many elements there are inside a set. So those are the two problems we're going to work on. We're going to start with two sets. And the two sets may overlap. They may or may not overlap, but in general they do. So we're going to draw them overlapping. And this kind of figure is called a Venn diagram, which I'm sure you have seen before. And so A could be all the students who like chocolate ice cream, and B could be all the students who like vanilla ice cream. And then the overlap is those who like both chocolate and vanilla. So given two sets, we can actually we can do operations on those sets, just similar to addition and subtraction, except for sets, they're not addition or subtraction. They've got special names. So the overlap of two sets is called the intersection. And it is represented by this cap symbol. It's sort of like a cap. And so it's called cap, or just intersection. And that is the shaded area of the diagram above. That's everything that's in both A and B. We can also form the union of two sets. So here's my universe. Here's my set A and my set B. And the shaded region, in this case, is the union of A and B. It looks like a letter U, but it doesn't have the descender, the downstroke on a U, so it just looks like a cup. Cup is the symbol. That's our second set operation. There's a third one, and it's just an operation on a single set. So if I have the set A, then everything that's not in A is what's shaded here. And this is a complement. It's everything that's not in A. In this here, I should have written out everything in A or B. So the key word in the intersection is and. The key word for the union is or. And the key word for the complement is not. And these are our three pictures. And this is pretty much it for basic set theory. There's a few other things we can do with set theory, but not much. It's a very general theory. It talks about very, general concepts of collections of objects, and those could be anything at all, numbers, people, stars, whatever. So the theory is not really very specific, and so therefore not terribly detailed or complicated either. But the interesting thing about set theory is that it provides a framework for us to try to count things. And so let's take a look at this example. We have our ice cream example, and suppose there's 35 students in the class, and we do a count, and it turns out that 18 like chocolate ice cream. And 21 like vanilla. So the question I have is how many like either chocolate or vanilla. Okay, so that is a kind of a math counting question. Now I could run through my class and ask everybody, do you like chocolate or vanilla? And then count up all the yeses. And that would be one way to answer the question. But what I'm going to try to do is to answer it with the data that's available to me now. So 18 like chocolate, 21 like vanilla. And so the obvious thing to do would be to add those two numbers up, and I would get 39 like chocolate or vanilla. And that is wrong because there's only 35 students in the class. So something is not right here. And the problem is, if we think about it, that I've double counted the overlap is what happens. So the students who like chocolate and the students who like vanilla, well, there may be students who like both chocolate and vanilla. And those students are included in this 18 and also in this 21, so I've double counted them if I just add them. So that's what happens. So what I need is one more piece of data, and that is how many students like both chocolate and vanilla. 10 students like both chocolate and vanilla. Now I can start to put that data into my diagram. So inside each part of the diagram, I'm going to put the number that are in that category. So the overlap of chocolate and vanilla has 10. That means there's actually only 8 people here who like chocolate but don't like vanilla. And there's 11 people here, right? So this number 18 has to be the sum of these two. 10 plus something is 18, and so that something has to be 8, and that's, I guess, why this discussion is included in the subtraction section of the course textbook. Similarly, there's 21. Well, there's 10 already in the intersection, so that means there have to be 11 more in this category of students who like vanilla but don't like chocolate. And so what does this give me? It gives me 21, 29. So I can actually figure out how many students are in this category here. So how many don't like chocolate and don't like vanilla, or like neither chocolate nor vanilla? And that's 6 of them because there's 35 students altogether. All right, so we managed to fill in each of the blanks in this diagram, in this Venn diagram, and we needed 3 pieces of data to do that. And so that's how these questions typically go. We can, I think it's best if you can try to work your way from the center of the diagram outward. Find out what is in the overlap, and then what is in each set, and then we can find out what is in this category on the very outside of the Venn diagram. All right, so actually I have to stop right now. I will be back and finish the rest of the lecture in a moment.